Welcome back, Algebra 3. We are in lesson 23, and we're going to talk about exponential functions. So we've already talked about a few different functions. We first have been, for the longest, talking about linear functions. And a linear function looks like this, right? It's just a line, a straight line on a graph, right? And then we began talking about some different shapes, and one of the things that we talked about just recently was when we have absolute value functions. So the absolute value function, those functions look like this. They look like a B. That is when you have the absolute value in that equation for the function. And then we went over in lesson 22, we talked about reciprocal functions. And reciprocal functions, they look like this. Let me write that out for us. Reciprocal functions. They look like this. They look like two curves that are back to back, and then they have that vertical asymptote that never touches the axis here or here or here or here. They just kind of let me see if I can do this a little bit better. They sort of live in this little curvy bit right here, and they never touch and they never cross. Their values never line up, right? They have those vertical asymptotes that never touch the axes. And that is what a linear, absolute, and a reciprocal function look like. So now we're going to talk about the shape of what we call exponential functions. And an exponential function is going to be a function that has the variable x in the exponent. So we would have something like y is equal to 4x. That is an exponential function. That is where your exponent of x, or your x, is your exponent to a base. And again, the number that that has the exponent is the base. And then the exponent, we call that the power. So the exponent here, the power is the variable x. So let's jump in and let's see if we can figure out the shape of the exponential function and what properties it might have. So in looking at 23.1, we have we've been given a function y is equal to 2 to the x power. And the best way, just like we learned with the reciprocal function and doing that, we learned the best way to figure out the points that we need to graph is to actually create our chart, our table that we usually use. So that's what we're going to do. We're going to put in x, and we're going to put in our function. Sorry, put that in the wrong spot. This should be 2 to the x, not 2x. And then that's going to give us our y value. So in doing these, we have to be very careful about what we choose for our x value, because it's an exponent. It's not a factor anymore. It's not a base. It is an exponent. So it's going to have a huge impact on the value of y. So I would always start with 0. You know, I always like to start with 0 anyway. But in this case, thinking about exponents, the first thing that you want to remember is that anything to the exponent of 0 is going to be 1. So 2 to the power of 0 is 1. So it doesn't matter what this base is at all. It's always, always, always going to be, if it's a whole number for sure, it is always going to be 0, 1 as a point in an exponential function. So let's say we pick 1. That's another easy one. If we put 2 to the 1, then it's just going to be 2, right? Well, what about -1? We could do 2 to the -1, and we know that would just be flipping it and making it the reciprocal, so that'd be 1/2. And if we did 2, we know 2 is an easy one to graph also, or an easy one to calculate. 2 to the second power, we know that would be 4. And then we could do the same thing to 2. We get -2, and 2 to the -2 would just be 1/4. Just be the reciprocal of that. So these are some pretty easy values, and that's 5 of them. That's a lot. That's a lot of points. So when we get ready, we can easily graph these. So that's what we can do. We can I'm just going to do a little quick graph here. And one of the cool things about exponential functions is that you do not have to have the bottom part. You really only need the top part. So let's see if I can make these fairly even. I'm trying to use my cursor here as a measuring guide to make these fairly even. Let's see if I can do it this way also. And maybe this way we'll put a few. All right, that's pretty good to get started. So let's begin. Let's do 0, 1. So this is 0, 1. And I think I'm going to zoom in a little bit so we can see this better. So here we go. All right, so that's 0, 1. So let's do 1, 2. All right, so 1, 2. Then we have -1 and 1/2. So that'd be -1 and 1/2, so it'd be right about here. Then we have 2 and 4. So 1, 2, 1, 2, 3, that'd be 4 right about there. And then we have -2 and 1/4. So that would be -2 and 1/4, even closer here. So what we're going to end up with here is another vertical asymptote on the base or on the bottom. And that's when we use our negative values, because that's going to cause us to have a reciprocal value there because of the negative exponent. And because of that, it's going to be a vertical asymptote that never touches the x-axis, but then the y values are going to increase exponentially whenever we have a positive number. So that's what we're going to see. The negative values create a vertical asymptote, and the positive values create a what's the word? A very steep, that's the word I'm looking for, a very steep curve the higher the base is, and the higher the exponent is as well. So that is what a exponential function is going to look like. So here's something else that is important to remember, and that is that it does not matter what this base might be. I mentioned it just a minute ago. You're always going to have this point 0, 1, because it doesn't matter what the base is. When x or the exponent is 0, the answer to y is always 1. So if x is always 0, y is always 1, because any number to the power of 0 is 1. So every single exponential chart or exponential function is going to have this point. And I wanted to show you something. Let me pull it up here. This is in your copy of the book. If I can get it to come to the forefront here. Let me pause and get that up for you. So I wanted to show you on page 168 here in the book. This is a like an illustration of several exponential functions, and they're given here. Here's y is equal to 2 to the x, and you can see that it follows right there. It follows along, and you can see that as the exponent base gets higher, then the y, where it crosses the y-intercept, that y asymptote gets steeper. It's not actually, well, no, it's not an asymptote because it doesn't get near. It pulls away, but the slope here is steeper when the base is higher, and as the base is lower, then it is it doesn't rise as quickly. It rises more slowly. So the slope is a little bit more, it's less steep here. Now also notice here that every single one of these exponential functions goes through the point 0, 1. Just like I said over here on our drawing. And that works when we have a exponent base, or an exponential base that is less than 1. What happens then is our function shape is flipped, and our vertical asymptote is in the positive side of the x, and our y is on the negative side of x, and it does the same thing, or actually no, it does the opposite thing. Whenever the value, the smaller the value gets, the steeper the curve, and 1/2 is bigger than 1/4, but yet it's steeper here than 1/2, right? Here we have 1.5, here's just 1/2, and you can see that it it slacks off. So I imagine if this was, I don't know, if our value here was 2 out of 3, it would be even steeper, because 2 out of 3, or even less steep, I should say, 2 out of 3 is a bigger number than 1/2. So I would venture to say that that would be a little bit steeper, or less steep even still, right? So that is what an exponential function looks like. So let's go through, that was 23.1. I want to check that on the Geogebra. So I've already got it typed in, y is equal to 2 to the x power. And if you look very closely, we can see that what we drew up in our graph is equal to what is here. Again, 0, 1 is the y-intercept every single time. And then we have those points. Here we have 1, 2, right? We have 1, 2, and we have 2, 4. So let's see, here's 2, 4. So that's another point that was called out. So you can see that they're there. What we graphed is there. So use Geogebra or Desmos or your graphing calculator to check your points and to check the drawing of your graph. It's going to make your life a whole lot easier. So we're going to do 2 more of these and then we'll be done. But I'm going to do them down here on graph paper where it's going to be a lot easier for me to do that. So let's start with sketching the graph of the function. This is 23.2. We're going to be sketching f of x is equal to 5 to the x power. Now note that we're using f of x instead of y. It means the same exact thing. It just means that we're giving this sketch of this function a name, whereas before it was just plain old y value. Now this is line f, or function f. So we're going to, again, use our chart because that is the best way to figure these out. We'll create our own little function machine and solve by subbing in for x. We'll solve for y. So 5 to the x power is what we got here. So again, we'll start with 0. Then we'll do 1, then we'll do positive 1, then we'll do 2, and then we'll do negative 2. All right, 5 to the x power, 5 to the 0 power is 1. It's always 0, 1, right? So that's our point, 0, 1. All right, 5 to the power of 1 is always going to be itself, so it's 1, 5. Yeah, I'm sorry, I got both the y there. 5 to the negative 1 is going to be 1 over 5. 5 squared is going to be 25. And 5 to the negative 2 is going to be 1 over 25. So we can easily find these. 1 over 5 there, 2 and 25, and negative 2 and 1 over 25. Okay, so these are our points. I'm going to do my best to graph these right here. And I'm just going to do a little bit right there. All right, I'm going to use blue because it stands out well. So this is 0, 1. It's always on that point, so you can always start right there. Then we have 1 and 1. 1, 2, 3, 4, 5. Man, that is a steep curve. Remember, we said the higher the base, the steeper this y ascension is going to be. Now we have negative 1 and 1/5. So that's going to be negative 1 and 1/5. Looks like it might be right about here. And then we have 2 to the 25th power, or 2 and the 25th point. So this will be on the 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh goodness, it's a lot. Let me see if I can get there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Nope, I'm not going to be able to get there. So anyway, it's an extremely steep curve. I'm going to go ahead and move this down and see if I can reach it anyway, just for funsies. All right, so if I move that down here, let's see if I can do it now. Oh goodness, I didn't move it right. I've got to put it on a line or my counting is going to be terrible. All right, so let's put that there. Excuse me. Okay. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's 20 right there. 21, 22, 23, 24, 25. I moved it down just enough. But we can see how steep that is. Oh my goodness, that is a very, very tight slope right there. So it's going to go all the way up there like that. And then this is going to be negative 2. And I mean, it's going to be right there. It's just minuscule. But we have this vertical asymptote on the left-hand side that gives us a very steep y over here on the ascension side. And I'm going to see if I can't pull that curve in here just a wee bit more. Kind of straighten that out a bit. So there's that. It's not so bad. But anyway, that is what we would end up with. And if you want, you can check Geogebra. We can pull this over and type this in. Let me delete this one. And I'm going to type that y is equal to 5 squared. Or, oops, sorry. 5 to the x. All right, when I shrink it down to where we can see it, we see how tight and steep that curve is. And we see that vertical asymptote that never passes and comes down below the x-axis. But that is a super, super steep curve right there, ascension of the y. So we got that correct. So let's do one more. Let me clear this. And I think I'm just going to leave it right here. We are going to do 23.3. And that one is, we're going to sketch a graph of the function y is equal to 0.25 to the x power. So again, we have to create a table, x, and then we're going to put in 0.25 to the x power, and then that's going to give us our y. So if I put in 0, then 0.25 to the 0 power, it's always 1. If I put in 1, 0.25 to the 1 power, that's going to be the 0.25. And if I put it into the 2 power, 0.25 to the 2nd power, I'm going to just pull up my calculator. Was hoping I already had it open, but I do not. Now this is less than 1. So this is telling me, because it's less than 1, it's going to be flipped, and our vertical asymptote is going to be on the positive side of the x-axis, and our y ascension is going to be on the negative side of the x-axis. So let's look here and see what 0.25 squared is, and that's 0.0625 is our answer. If I have -1, then 0.25 to the -1 would be 1 over 0.25. And the same thing for -2, I would have 0.25 to the -2. That'd be 1 over 0.0625. So let's just check our points with GeoGebra. For the sake of making sure we got it done right, I'm going to delete this one. And I'm going to put in here y is equal to 0.25 to the x power. And look at just how steep that is. Oh my goodness. Let me close this. If I scroll in, like enlarge this, you can see that this is going to be super steep as well. Right? And again, looking here, we always have that point 0, 1 where it crosses. And our next point would be at the 1, 1, and oh, that's -1, sorry. X is -1, and we have 1 over 0.25 here. This is 4. Oh, 1 over 0.25. Okay, so why would that be? Why would we do that? Well, let's look at our problem. We have a decimal down here in our denominator. 1 divided by 0.25, that's going to equal 4, right? So yes, it does have that fractional value, but don't forget to take it further. So I forgot to take it further. So that's going to be 4. And if we have, let's pull up a calculator, 1 divided by 0.0625, that's 16. So that is going to be 16 is the value here. So I just did not finish this right here. I got it to a certain point, but then I didn't stop it. So that's what happens when you have a decimal in the denominator. And this ends up being a larger number. It should be -1 and 4, -2 and 16. Okay. All right, so that's pretty fun stuff, but we can see exactly where that number gets us to and how that works. So whenever you do this, be sure to not leave decimals, if you have any, in your denominator. Instead, go ahead and divide 1 by whatever the decimal is to get your whole number, or to get your value here. All right, don't, what's the word I'm looking for? Don't hesitate to check your work with GeoGebra. This is a way that you will be able to know that you're doing it right. So when you pull up the graph and you see something that looks like this, and you say to yourself, -1 is on the 4. What did I not do? You can go, oh, well, That's a decimal. It's not supposed to be in the denominator. Of course I'm supposed to divide that. Of course 4 times this is equal to 1. Ugh, why didn't I think of that? It's going to help you check your work and get you where you need to be, all right? Which is exactly what it did for me. So don't hesitate to use it to check your work. Don't use it to do your work per se, but you can check your work with it, all right? And that's all we have for lesson 23, and I will see you in lesson 24.